All right. So, welcome back. After last session, we're going to continue this Thursday and with scheduling. All right. So, so last session we talked about your Pinterest project number 1. Asif and Vivek, I think if you're, you don't, yeah, you're done. I guess I'm going to start the lecture. All right. Thanks. Yep. Thank you. So last session we covered project number 1 and then talked about the steps that you have to take, implementation and design document, and everything is out on the piazza. So do you have any questions regarding project number 1? No? All right. So today we're going to talk about, first going through assignments. So I still have seen some of the students have not formed their groups. They're not registered on the GitHub Classroom. So please do so because we need to take care of the rest. So if you have a group, register it as soon as possible. Otherwise, we think that you don't have it, and then there are a lot of students. So and I think I saw a couple of notes on Piazza that were regarding the groups. So if you still don't have a group, make sure you post it on Piazza. And so today we're going to talk about CPU scheduling. Today we're going to cover some basic concepts of scheduling and what are the metrics for scheduling and different algorithms. So these are very important, especially for your first part of the semester before for your midterm number 1. Okay, and we're going to talk about preemptive and non-preemptive scheduling. And how they're compared against each other, like these algorithms, all right? So we have talked about multi-threaded and multi-programming, basically, when there are multiple programs or processes running at the same time, time sharing, and so what matters here is now how we can schedule these, between each other, like what should be the correct way or the best way, at least, to approach that. So the CPU scheduling is the short time scheduling, and that is to basically decide which process should execute next on CPU. And if you remember, processes had some CPU bursts and then I/O burst, meaning sometimes they want to run something on CPU and sometimes they're waiting for I/O, right? And so basically, they're always, each process, if you look at it as an individual process, they're always in a cycle between CPU burst and I/O burst. So, for example, they do some calculations or memory access, and then they want to read something from the file, and then they have to wait for the I/O. Once that information is retrieved and ready, and then they again do some calculations or process, and again they have to wait to write on a file or wait for a device, right? So they're always in this cycle. And so if you take a look at the CPU burst durations of different processes, you get a histogram like this. A lot of processes are not very CPU intensive, but they have short bursts of CPU and then doing something with the I/O, and again short bursts with the CPU and again waiting for the I/O, right? So most of the cases they have very short bursts. Most of the time they're waiting for I/O, and again this is relative timing, right? CPU is pretty fast, right? So compared to what an I/O has, if you want to wait for 1 or 2 milliseconds even for something, that's just a lot for CPU, right? So if you want to wait for actual reading something from hard drive, that takes a long time, right? So, and for this, the processes have now to change, right? After one short burst, the other one. And so this is a slide from previous lecture on processes, and it shows us different states of a process. You remember, when a process gets created, then it goes to a ready queue, and then it gets scheduled into running, and then it might again get interrupted or get blocked because of an I/O, and then go to waiting. Once the waiting event happens, or the time is over, whatever, they go back to ready. And so this is the overall cycle of a process state. All right. So now there are what the CPU scheduler does is that it basically from each of these events or states might cause scheduling, right? The scheduling happens either when a new process arrives or when it switches from running to ready. We're going to talk about each of them now. Switches from waiting to ready, switches from running to wait and terminates, right? So I think this is clear. When a new process arrives, right, a scheduler might schedule it, right? And this is like preemptive, meaning if another process is running and a new process arrives, right, this is involuntary for the running process. So if the schedule happens, it has to preempt the running process, okay? So now if we switch from running to ready state, when can this happen? When a thread is or process is running and then suddenly we want to preempt it and put it on the ready without another process arrival. This can happen, for example, when the time quantum is over, when the OS decides that okay, it's time for you, or a new interrupt comes and the OS decides that it has to do something else. So the running thread has to be preempted and put back on ready list. So if a process now goes to from waiting ready, so let's say a process is waiting for a timer, and the timer now ticks, and so the time, the elapsed time is over. So the OS now wants to schedule the sleeping thread. Now, when the OS wants to wake this up and schedule it, there is the running thread, right? The OS has to preempt it and stop it, put it back to ready list, right? So, and also, so this is when this is from waiting to ready, and when a process switches from running to waiting state. So, brain freeze. So when the running process goes to a waiting, this is non-preemptive. The reason is, let me just cover this next two and then, right? So it means, for example, when a process itself wants to go and get blocked. If a process wants to wait for a timer, if a process wants to call a system call, when a process wants to do an I/O, right? Basically, the process itself tells the OS that, hey, put me back on, sleep or waiting list. And so it's basically non-preemptive. It's cooperative. And a schedule again might happen when a thread or process terminates. When a process is done, it will tell the OS that, hey, I'm done, just clean me up. And again, the OS now needs to schedule another process, but again, it's not preemptive. It's just like voluntary by the process itself. Go ahead and ask. Preemptive and non-preemptive. So preemptive and non-preemptive is the way that the OS is treating the running process, right? If a process is running and the OS forcibly takes it out, that's preemptive. That's called preemptive, right? So because you remember, the processes don't have any idea about like what the OS does, right? They are working on their instructions, and when the context switch happens, when the other processes get scheduled and back, they won't realize it because they are just like frozen right where they are. Put them back like a statue by the OS, and then once again, like it's their turn, they're put back, and then again they just keep running. So they have no idea if they have been interrupted, right? So, but preemption is important because there has to be precautions because basically you're taking this process out. Now, what if this process has accessing a shared data? We talked about it last session. So if this process is accessing this shared data, and another process also wants to access this shared data, right? If you interleave them, if this process is halfway done, then the other process accesses something which is halfway done, right? It's not finished by the other process. So, we have to now, preemption is important, for example, because of, these things. So if a process itself reaches a point that is not in the middle of something, right? That's non-preemptive. So again, as an example, if a process wants to access a file, right? So it's not in the middle of something. It asks OS that, hey, retrieve this information from the file and let me know when you're done. This is not, in the middle of something. They want to wait. So the OS, keeps them waiting. Once they're done, give them the information and then ask, give them back the CPU, right? So this is not preemptive. So the OS is not forcibly taking them off the running state, right? Any other question? Was that clear? No? All right. So in the case of 4 and 5, which is the wait and termination, These are non-preemptive, right? But so that means that once a process gets the CPU, they keep running until they decide when it's time to be paused, right? But the other ones are preemptive, and that means a lot of OSs use these because you don't want to let the one process decide when it's time to schedule, because maybe they just keep running, maybe they freeze up, right? So a lot of the times you need these. And so, for example, what we have discussed is a time quantum. So even though maybe you're not done, maybe it is time for you to at least set aside for some time, let the other processes run, and then we'll schedule back you in. But as I said, it is important when you want to access shared data, because again, the one process wants to do something which might be again required by a different process, shared data, right? So if you, as an OS, want to forcibly take it and have it paused, what happens to that shared data? Because the data will be there. It's not that data is now inaccessible, right? So again, if it's an intermediate state of that data, the other processes can't tell. They take it as is, right? So simple example would be just if there is a roster of this class and this process now wants to replace this roster with a roster of a different class, right? Well, it doesn't do it like all together. It does it one by one. Now in the middle of it, if you take it and now a grading process wants to now take the roster, it's nor the roster of this class nor the second class. It's somewhere in between. It's like a corrupted file, right? So you don't want that to happen, and the OS is responsible for this because the OS is forcibly taking the processes out of the running state. So the dispatcher now is basically when a process context switches, right? So the scheduler decides when or which process should be running. Now the dispatcher basically switches the context between the processes, freezes this one, as we say, save its states in the process control block, retrieve another process control block, and then basically then switch it back to user mode, and then jump to wherever that the program was paused, right? You remember in the process lecture we talked about each process always resumes, right? So when a dispatcher wants to bring a process, that it has to resume wherever it was left off, right? And that basically needs some kernel access. After that, after the context switching, then the kernel switches back to user mode and then jumps to that instruction that was like paused. All right? So, and then this has a latency. This is important because this latency is part of the overhead, right? The scheduler also has to decide which process should run next. That is also overhead. But this is also the dispatcher latency itself, which is again overhead. And we want to minimize this, right? Right? So now the scheduling itself has some criteria. It has to consider a couple of things, and then there are basically a lot of like trade-offs. And so we want to see what are the goals of a scheduler, right? So what is the CPU utilization? It's when keeping your CPU as busy as possible, right? So what does a scheduler should do? Should it decrease the utilization or increase the utilization? Increase, yes, because you don't want the CPU to just like be idle, right? You want to actually use it, right? So the scheduler should maximize this. What about throughput? Throughput is the number of processes that complete their execution per time unit. You want to increase it or decrease it? Increase, obviously. So now response time, amount of time it takes from when a request was submitted until the first response, not the output, but the first response. Basically, when a new process, for example, gets scheduled or becomes ready, the amount of time between that arrival until it gets the CPU for the first time. So what do you want to do with this? Less time. You want to decrease it. It's better, like a CPU scheduler should not keep the other processes waiting, right? Waiting time. Total amount of time a process has been waiting in the ready queue. Not just the first response, but overall, because you might like have a, you get the first response, you do something, and then you will go back to ready list and wait for other processes, right? So, but again, you have to like get scheduled back in and then out, and then again in and out. All the times that you wait is called like waiting time. You want to also so minimize this one. How about turnaround time? Amount of time past the finish execution of a particular process. It's basically from your arrival time when the process is created until it is done. The scheduler wants to also minimize this, right? You don't want the whole process to just take forever, right? So the turnaround time is the execution time or burst time plus waiting time. So, that I just added in this time. Execution or service time is the same thing basically, right? That's when the CPU is servicing that process, right? So this is a summary. So the scheduler wants to maximize CPU utilization, maximize throughput, minimize response time, waiting time, and turnaround time. All right. So let's see. These are what the scheduler metrics are called. So one is arrival time. It is the time when the process just becomes ready. It might have been, waiting, so it becomes ready again, or it might just be its first time. It's newly created. After the creation state, it goes to ready state, right? So it's called TA. And then there is a wait time, which is the time spent waiting for the CPU. And then there's service time, which is the execution. And then turnaround time, which is waiting plus executing, right? So let's take a look at this diagram. So there are different processes already there. And the process number 5 arrives at this point. So this would be its arrival time. And then all this time that is not running on CPU, it's waiting time. And once it's executing, this is service time. And then from the arrival time until the finish time, this is turnaround time, right? And so in this case, the turnaround time ratio on service time ratio is 2.5. So this is one metric because it basically gives you an understanding of like how much relative to its service time a process is taking. So if a process is taking only one time, it basically running on CPU for 1 millisecond, but from when it's arrived all the way till end of it, it's 100 milliseconds, then your scheduler is not doing a very good job, right? Because that shows like how inefficient it is, right? So this number should be as close to 1 as possible from the point of view of the process. Any question on any of these? So this waiting time, by the way, here in this diagram is just like one consecutive waiting. It might not be, so we will see in the next examples. Again, waiting time is total time that the process is waiting. So in this example, the waiting time and response time is basically the same thing, because once it gets the first run on the CPU, it just executes the whole process. So now there are different scheduling algorithms, right? We want to dive into each of them. So the first one is first come, first serve, right? FCFS. And that is like, I think, easy to understand, and it's relatively fair. We're going to go back to, we're going to cover their pros and cons in the end. But so any process at any given time, if a process comes, it goes at the end of the line, and then the scheduler basically picks the first one, executes it until it's done, and then picks the next one, right? So here, for example, in this example, we have arrival times like this. A comes here, and then B here, and then C here, D here, E here, right? So what does the scheduler do? This is exactly the process that you should do when you want to, like these diagrams will be part of your tests or homework, right? And you have to understand how to approach them and make it easier for yourself, right? So have it always have the arrival times, clear like that. And then just like, go chronologically, starting from time 0, and then again, just be the OS, be the scheduler, and see what's going on. So at this point, what you have is just A, right? So you schedule it. And then you go ahead. At this point, the B gets, in the queue, but we are in the first come, first serve, so we don't care, right? We keep running A until it's done. When it's done, well, we know the burst time, right? It's 4, so at this point, it's done. At this point, B is there in the queue. So we pick it up and then schedule it. So B gets all the way, up to here. Once it's done here, what do we have here? We have all the C, D, and E. Each of them are, again, in the queue. So we first schedule C, after it's done, D, and after that, E, right? And so this now shows a little bit of some of the information. So finish time for A would be 3, B is like, here, 9, and then C is done here, which is 18, and then D is here, which is, 13, 18, and then 20, right? So this is the finish time. Now, what would be the turnaround time? You remember, from arrival to finish. Right? So if A is here and then finishes here, so the turnaround time is 3. B arrived here, finished here, so 7. C arrived here and then finished here, so that's like 9. For D and E also you calculate that, 12. And then the ratio between the turnaround and service time, again you calculate it. What is the turnaround time and then what is the service time? You already know from here, and then you just divide them and you get these numbers. And then there is the mean. Yes?
What happens if there are dependencies between the processes?
We're going to talk about them. Each of these, when we're talking about, they are basically chunks of the processes that are ready to run. If a process is not ready to run, it's not in the ready list. So it goes back to a waiting queue, and then once it becomes ready, then we figure out, okay, now for how long you want to run, right? So each of them for now, it's just like simplified. They're independent. We don't, again, like this is what we cover here is not the total time that actual process A might, run in the span of, a day. For that chunk that is CPU burst, what is the number? So then the mean values show a little bit of, how the scheduler is doing, right? So in this case, the turnaround time divided by service time is 2.5. It's not very good. And the mean turnaround time is 8.6. So now this is an example. So let's say we have like 3 processes and their order is like P1, P2, P3 for now. We don't care about like exactly when, but it's first come, first serve, so we already know. And their burst time, let's say if they're like 24 and 3 and 3. What is the Gantt chart? This is something that you need to know and then draw a lot, right? So when the order is like again first come, first serve. So P1, P2, and P3, P1, P2, and P3. P1 runs for 24. P2 runs for 3 units of time, P3 also for 3 units of time, right? So what about the waiting time? So process number 1 didn't wait, right? So it just like was 0. Process number 2, again, assuming that they arrived, all together in the order of P1, P2, P3. P2 waited for 24 units of time before it get the response, and then P3 was 27. So if you average it, then that's like 17 in this example. Now, what happens if you change the order of these? Now, if you change the order only to P2, P3, P1, the same process is running. So you still have 30 units of time of CPU time, right? But your waiting times are now much different because your P1 is 6, P2 is 0, P3 is 3. And if you average it, now it's 3. Same processes, just different order. Your average wait time goes down from 17 to 3, right? And that shows like how dependent on this order can be. Again, remember, all of them basically received at time 0, right? It was just like a different order. So this is what we call the convoy effect. When short processes wait behind a long process, this is not good because they're just like the average wait time is like getting up, right? So this is like, for example, in a highway, right? If you want to take over all of them and then they're going all slow and then you have to just wait for them to go and it just takes time. But you already kind of know what's the solution in the highway, right? In a lot of cases, like if there's a trailer and it's just like one lane, at some point there are like so many cars behind them because they're going slow. And well, if they're considerate, every now and often they, get off the road shoulder so that the cars can just like empty the line and then they back up, right? So you already see what the problem is and kind of the solution, right? So the next scheduler is any question regarding the first come first serve? So the first come the shortest job first is basically when the scheduler decides the process that has the least burst time should get scheduled. It looks at the current ready list, and then based on the burst times, it picks the one which is the least of them, and then it schedules it and let it run until it finishes, and then picks the next one. Yes?
How do you know it's the shortest?
That's the good question. We're going to talk about it at the end of this slide, and then more in depth in next session. Because basically it's unknown. So there are 2 ways to do this. Either it's non-preemptive. As I just said, it's simple. You pick the shortest one, let it finish. Non-preemptive. Once it's finished, you pick the next one, right? So preemptive is now you pick the shortest one, but maybe during the execution a new process arrives, right? So then maybe that new process has the shortest remaining time, and then you have to schedule that one, right? So even at this point, between these processes, let's say there are like 10, 12, and 14. You pick the 10. After 5 units of time, a process comes that its burst time is only 1. So at that point, the current running has 5 more units of time. That is only 1. So that is actually the shortest, right? So you can schedule it, preempt this one, let that one finish, and then come back to this one. Or again, at that point, whichever that has the shortest remaining time. All right? So this is, you might see it as SRTF or just SJF preemptive. Just get yourself familiarized with the terms and acronyms. All right? So the problem is that, yes, it assumes that you already know the burst time, which is not known. There are ways to estimate it and approximate it, and that we're going to talk about in next session, right? But considering you have a short, you know the burst times, SJF basically provably has the least amount of average waiting time. Yes?
So for example, that means that like 10, 11, 12, right? So let's say I do process training, that's 5, let's say. It'll skip the line.
Yes. Yeah.
Now what if the 10 passes to 5 seconds now?
The 6 comes.
6.
Yeah. So at that point, when the last process comes, so his question is now when we have like 3 processes, 10, 12, 14, again the same example. Now we pick the process with 10 burst time, and now it runs for 5 units of time, and now a process comes. If this process is 4 units of time, remaining time for this one is 5, the new process is 4, so that has to get scheduled. This goes back to line. When that one runs, then this process now is 5, the other one is 12, and the other one is 14, so we go back to the one with 5. Now if the new process comes and its burst time is 8, so the running thread is now 5, the new process is 8, the other processes are 10 and 12, or 12 and 14. So right now there's no need to preempt it. This one running has the shortest remaining time, so it keeps running until it's done. After that, now the scheduler looks at it. We have a new process with 8. We have like 12 and 14. So the 8 will get scheduled after that. All right? So SJF again has the average, the minimum average waiting time, but it has its own issues as well. First thing is that we don't know. So this is an example for this. So consider the processes come in the at these times and then what the schedule does. So this is for non-preemptive for now. So meaning we just pick one and then let it finish. So at this point we only have like A. So we pick one and let it finish. At this point what do we have? We only have B, right? So again, we pick it and let it finish. By this time C, D, and E has arrived. Which one is the shortest? E. So we pick E and let it finish. And then now we have C and D in the queue. Which one of them is shorter? C. So we schedule C, let it finish. After that, D, and let it finish, right? So if you take a look at the finish times now, this is like, 3, 9, 15, 20, 11 and 20 for E and D. And then the turnaround time is from arrival to their finish. So 3 is 3, A is 3, B is from 2 to 9, which is 7, C is from 4 to 15, which is 11. D is from 6 all the way to 20, and that is 14. And E is from 8 to 11, so that's 3, the turnaround time, right? So, and if you look at the ratio now, it's better, and the mean time, average waiting time is less. This is not calculated in this one, but we're going to calculate it in the next example. Yes?
But Professor, then if that's the case, then non-preemptive and preemptive would take the same amount of time at the end, right?
Well, the total time is the sum of all the burst time in all of these.
Yeah.
Because the CPU, in our examples, we usually don't keep the CPU idle. That might be the case. You have to make sure. So at this point, for example, when A finished, if B was not there, where this time slot the CPU would be just idle, right? But considering all of them are running after another, well, the sum of the CPU time will be just like the sum of their burst time. So the scheduling algorithms just basically change the average waiting time, turnaround time, average turnaround time.
Do we not consider the time for scheduling in between these?
Come again?
Like, do we not consider the time for scheduling?
No. The overhead is not here, and that should be the case. Usually, the overhead of scheduling should be so much little that basically we should be able to ignore it. Sometimes it's not, but at least in this example, we want to keep it simplified, right? All right. So this is an example. So let's say a process. These are the processes, and then their arrival times in the order 0, 2, 4, 5, and then their burst time we already know. So 7, 4, 1, and 4, right? So remember, it's shortest job first. Chronologically, always think it that way. So at time 0, we only have process 1, and then it goes like to 7. It's non-preemptive, so it has to run all the way to 7. At time 7, what do we have? Well, this one is finished, and we have all the other ones. Which one is the shortest one? P3. So P3 gets run for 1. After this, what do we have? Again, all of them, 2 and 4 are ready, with a burst time at 4 and 4. In the case of a tie, in most of the other algorithms as well, even whatever, like priority, shortest, if there is a tie, we still use the first come. So between P2 and P4, we schedule P2 just because it got to the queue a little bit sooner than P4. It runs for the 4 burst, and then P4 gets scheduled for the 4. Yes?
This will cause starvation.
That is very good observation. Yes. We're going to talk about it. This is one of the problems with the shortest job pairs. Yes. So the average waiting time for these is now, so P1 was 0, P2 is like 8. Wait, what? Okay, maybe I made it wrong on this one. This one should be 8. P3 is 7. And so 15 plus 12. Oh, no, sorry. This is waiting time, not there. So we have to subtract the arrival time. So from 0 to 0 is 0. From 2 to 8 is 6. From 4 to 7 is 3. From 5 to 12 is 7. Right? Don't make the mistake that I did, right? So you divide it by 4, and then now the waiting time is 4. So this, I think, is the same as this one. No, maybe it would be in the next example. So, but the average waiting time basically gets minimal. Now, a preemptive, as we said, is just like the remaining time. At any given time, the scheduler decides. But any given time is when an event happens. When your ready queue is as is until a new process comes. So usually it's just like the same way, but at the times that the new processes arrive, you have to re-evaluate. So at this point, for example, A gets scheduled. Normally, you would think that it goes all the way to 4, but all the way to 3. In this case, also it would. Why? Because at the time that B arrives, it re-evaluates. How much left is from A? 1 time slice. How about B? What is that? 13, no. 1, 2, 3, 4, 5, 6, right? So it doesn't need to preempt A. It just let it finish. At this point, B starts. When the B starts with the burst time of 6, here, it runs, but at this time slice, C comes. Now the scheduler, again, reevaluates. At this point, B has 5 time slices remaining. What about C? C has 4 time bursts. So we have to preempt B and schedule C because this is the shortest. It runs up to here. Even at here, we have to reevaluate. At this point, when D arrives, we got to check. So at this point, well, we don't have to check the previous ones. We only need to check the new ones because the previous ones didn't change, right? And because this process that is running was already shorter than them, so we don't have to make any comparison. So at this point, when C is running, it has 2 more time slices left. What about D? D has now 5, so we just keep running. After this is finished, we take a look. We have E, B, and D all waiting. From these, E is the shorter one, so gets run. After that, B, the leftover of B continues and then finishes, and then D gets scheduled and finishes, right? And so again, they're just like some stats, and usually, again, this gives you a better number in terms of here, but not be fair to each individual process. Any questions for this one? Is it clear, the process, that how you should like, put them, in the order? Good. And just a suggestion, when you want to like, draw Gantt charts, try to do this. Don't just, think of it like, because you probably mess up. There's a chance. So make sure you actually draw just vertical lines. The easiest way is to just sum all of them, and then see, okay, like, this bird like has 4, this has 6, this has 5, and then total time that the CPU should run is like 30 or 20, for example, in this case. And then you draw all the lines, and then just like start drawing between them. Okay. So, and this is an example with the same processes, arrival times and burst time, but now this is a preemptive one, and this will result in a smaller waiting time, average waiting time. And then this is because again, the process that you didn't schedule because you didn't preempt the running process is having some wait time, which is more than this one. Okay, this is so I'm going to go just compare them similarly here. So you see, when process 1 keeps running from here, right, and then process 2 comes, so process 2 is waiting for P1, right? Now, if you preempt it, then process 2 gets scheduled, and P1 is basically waiting for P2, right? Either this one is waiting for the other one or the other one, right? But remember, at this point, we decided to schedule P2 because P2 is shorter. So the amount of time that, in this case, P1 is waiting for P2 is less than the amount of time that P2 is waiting for P1 in this case. So that's why it will bring the average down. And that was just like with the comparing two processes. Now you give it more processes, and then basically that's happening, right? So even though P1 is waiting longer in this case from here all the way to here, but all the other ones are benefiting from this, and then that's why the overall average will come down. All right. So the next scheduler is a priority scheduler. We mentioned this in project number 1, and that is one thing that you're gonna implement. So this is when you assign a number to each process that is their priority. Now in the book and textbook and the lecture slides, actually the smallest number is the highest priority, and your Pintos priority, it's because it's based on a 4.4 BSD scheduler, that actually the higher number is priority, the most, the highest priority. So just make sure you know which one it is. Again, in the class, in the lectures, we take the priority to 0 to be the highest priority. In your Pintos project, when you read the documentation, it tells you that the 63 is the highest, 0 is the lowest, right? So this is something that is defined. Now again, priority has also two schemes. Either it can be preemptive or it can be non-preemptive. So I'm just going to move here. Too tired of there. So in non-preemptive, again, it's kind of like what we see in the shortest job. Once a CPU is assigned to a process, it just runs till it finishes. After that, again, the scheduler decides, okay, now who has the highest priority? I'm just going to schedule that. It becomes more difficult when it is preemptive. So again, when a new process arrives, or later on you will see that the priorities might change during time, the scheduler should reevaluate. Now who is the highest, right? And so the shortest job first, these are pretty similar, because shortest job first is basically a priority scheduling where the priority is not a fixed number integer, but the CPU burst time, right? And the lowest one again has the highest priority, right? So this priority is, here we say when the priority scheduler, we always give a number, integer number, makes it simple. But the general idea is, the priority that you define, right? In the case of a short job first, it's the burst time. Now the problem also with this one is a starvation, because maybe a higher priority thread or process is just like runs. It has like also a long task to do, and then there's just like low priorities behind it that will never run, or they might just like wait forever, or new higher priorities keep coming, This is the difference between this one and the first come first serve. In the first come first serve, once you are in the queue, you are guaranteed you will get there. It might just take some time. In the case of a priority, you might not. You might just, like, a low priority process is there, and then new processes just keep coming with higher priorities. This will never get run. All right? And this can also happen in the shortest job, where again, long process is there, and then short processes just keep coming. Never they get assigned any CPU. So the solution to this in the priority case is aging, right? You get priority to the aged processes. As a process ages, they, like, basically get a bit of a get a head start, or they get bumped up in the queue, right? So that's where the priority is dynamic, basically. Any question in the priority? No. Yes.
Who decides priority? Is it the process themselves or the CPU?
Good question. Who decides the priority? This is one of the problems with the priority scheduling, because you don't know. Like, the OS can't tell based on something. So that's why initially, a lot of time, it's either assigned a fixed priority, or assigned by the process themselves, or based on their history, for example, or the type of the process, or the parent process. These are all the things that can decide the process priority. And then the aging also decides if, in this case, aging only brings up the priority, but in some cases you bring down the priority, so to balance things out. Yes. Usually, again, in the case of a tie, you do first come first serve. So if you are doing non-preemptive, you have to let them, whatever that was picked first to finish, and then the next one. In the case of preemptive one, I would say probably when the new process comes. This is actually there should be a tiebreaker rule in the case of a preemptive. So if a high priority is running and then the same high priority comes, should you keep that previous one run and then let finish, or you should schedule this one? In the case of a 4.4 BSD scheduler or a multi-level queue, then you have a queue of high priorities, and each of them are all of higher priority compared to other ones, right? But amongst themselves, they have a time slot, that they can switch. All right, which is the next one, round robin. So this example, again, the same processes. Besides burst time, they have priority. Again, you have to think of their arrival time and priority, right? So you can't just pick this one because it has the highest priority, because, well, this is not arrived yet, right? So going from 0, you have like two ways, either non-preemptive or preemptive. Let's say non-preemptive. At 0 time, you only have P1, so you have to schedule it and let it finish. By the time that it's finished, it's 7. All the other ones arrived, right? So what will be the order of the next ones? 1 has the highest priority with the lowest number, and then P4 with the 3, and then P3 with 4. Don't confuse these. Again, sometimes the questions might be, they're not really designed to trick you, but sometimes this is just the case. So the order of the scheduling would be P1, P2, P4, and P3. How about preemptive? These two supposed to be two different slides, but I think they're just like one. So in preemptive case, when the P1 gets scheduled, because it is the only one, it just keeps running until the next one comes. So at time 2, we reevaluate the ready processes and their priorities. So at this time, we have this one with higher priority than this, so we have to preempt P1 and then schedule P2. So P2 runs, and then when the other ones come, they have lower priority, so we don't care. So it just goes all the way to 6, finishes. At this point, among the other ones, well, P1 still has the higher priority, so it continues for the rest of the 5 times units, and then P4 and then P3. All right? So again, the same principle. Just start at 0, move on. The events are either finishing of a process, arrival of a process, and then just decide what is need to be done. Any questions? All right. So what's the slide number? Round robin. Round robin is very simple. This is what we have talked about, and that is when you have a time quantum, you assign each process a bit of it, and then chunks of time, and then it's just like a queue, one after another, right? Each process gets some time of the CPU, and then the next one, right? So then it is preempted by the OS, and then the next one is put there, right? So if you have like n processes, each one takes chunks of queue, quantum times, and then wait for the rest of it, right? So each of them technically will get basically an nth of the CPU time in chunks of queue, and then each of them won't wait more than this time, right? Because again, they're waiting after another time. So if you have n processes, the last process that gets scheduled will be scheduled or gets its first response after n-1 quantums, right? Because again, it's a queue, so when you are in the queue, you will get your response in time, and that is just like the order. So what about the performance? So what happens is if quantum is large? What happens if the time quantum is small? Anyone? Any guess if the time quantum is just very large? You can think of an even extreme. What happens? Yes. It becomes a first come first serve, right? If the quantum is too large that all the processes will basically finish in their quantum, it will be just like first come first serve, right? What about the small? What if the time quantum is too small? Now someone in the back told me I have a lot of overhead, exactly, because the number of times that you have to switch the processes is just too high that you're just like wasting CPU time on that, right? So you have to decide what is this quantum. This is very important. This is the problem with the round robin, because the quantum time is not clear. So this we give an example with two different quantums. This time quantum, by the way, in your Pintos project is defined in thread.c as time slice, right? You might just come across it. It's 4 ticks. I don't think it matters that much, but so when A comes here, it just gets scheduled. At this time, B comes, and because now B is in the queue and A was running, and A already had more than a time quantum, which was like 1. So then you put A back in the queue, and then B runs. B runs for 1 time quantum. After this point, well, A is again in the queue. You schedule A. After this point, well, C is arrived, so C is at the end of the line. So, but B is already in the line, so B gets to run for 1 time quantum. After this time quantum, B goes back to the end of the line, which now has C, A, well, A is finished, C and B. C gets to run for 1 quantum, and again, at this point, D has arrived, but B was already in the line. So now you have C, B, and D. When C takes its own time quantum, goes back to the end of the line. This actually would make it clear to write down on the blackboard, but we have like exercises. If you get the time, we'll do it there. For now, just consider this one. So once the C is running, again, D gets to run. C and B are not finished. They are in the order. So D runs. At this point, we have C in the line because B was running. Like C was before B, so it should be ahead in the row. And it would get a little bit difficult. So a lot of the cases, when you want to solve these, you need meta information, like meta, you have to write down at each time slice what is the queue looking at, like, right? So after D, E arrives here, but it's at the end of the line. The first would be C, and then B, and then E. So you assign C, and then B, and then E. Now again, it's just like one after another until each of them gets finished, and then they will be out of the queue, and then you schedule the rest of them accordingly. All right. So if you take a look at the stats again, it's just like that. Usually it doesn't give you a very good average turnaround time because it's just like interleaving all between each other. So they kind of like progress together, right? So that basically causes all of them to finish somewhere in the future, late. So the average turnaround time is not very good, but the response time is good because, again, no matter when you arrive, you probably get like assigned some CPU time quickly. All right. So now in this case, we change the time quantum to 4, and then you'll see basically that each of them get to run for 4 quantum until they're finished. And then in this case, you have like different results. So the time quantum selection is a crucial decision in this one, right? And we didn't show that in here, but the overhead is also there. So in this case, we have like what? 1, 2, 3, 4, 5, 6 schedules. In this case, you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, what? Like 16 or 17. So each of them has some overhead, which is usually relatively much smaller than this one. But again, you usually don't have like only 3 or 4 processes. There are tons of processes running, right? So you don't want to waste a lot of CPU time. And if you again, the queue is too large, they keep running like first come first serve. Or if it's too small, then it's just like it says it should be less than this, so otherwise this will happen to first come first serve or the other one. All right, any question in the round robin? All right, so this is another example. So considering the time quantum is there, you should always be given the time quantum, otherwise you can't tell. So the processes are these, and then consider they are all in the same order, but available at time 0. So once you have like P1, P2, P3, P4, you assign them in the queue, P1, P2, P3, P4. P1 gets scheduled for 20 time slots, and then at this point it has 33 remaining. P2 runs, but it doesn't run for 20. Remember to always check with this. P2 has 17 remaining, so it only runs up to this. P3 runs for 20 more, and now it has like 48. P4 gets to run, and that now has 4 more left. And so these are not very proportional, just, after this, we go back to P1. P1 still has 33, so it gets to run for another 20 time units, and then now it has only 13. And then after that, P2 is done. P3 gets to run. It gets to run for another 20. Now it has 28. Now P4 gets to run. It only has 4, so it goes only up to this. P1 gets to run. It only has 13, so it adds up to this. And then P3 and P3 again. All right? So again, the turnaround time is usually higher, but the average response time is good. So it's good for time sharing or interactive processes that they don't want to wait forever for their first response. And this is the context switch numbers. If the quantum is the larger, the context switch happening is the smaller. As you bring this down, this goes up, and this is the trade-off for the round robin, to decide what should be. And also, as you change it, it's not very clear. Like it's not linear, either increase or decrease in the turnaround time. Just because, right? It's just like complex. It depends on the arrival time. It depends on the burst times. You just have to sit down, calculate, and basically you see that based on different quantum times, then the average turnaround times just changes, and you probably can't know this ahead. So this is an exercise. Consider a system using round robin scheduling with a fixed quantum queue. Every context switch takes s milliseconds. These you should understand to be able to compare these, right? The overhead and the execution time. So if you have t burst time, what happens? Determine the fraction of CPU time that will be wasted in terms of s, q, and t, right? So let's see. If t, meaning the burst time of the processes, are much less than the quantum, what will happen? You already gave the example. If the quantum is larger than the t, it's a first come first serve, right? So in the case of a first come first serve, then the fraction is that you have one context switch per process, right? So one context switch for process time plus context switch. So that's s divided by t plus s. So if t is too large than q, meaning each process gets chunks of q, and then for each chunk they also get one overhead, which is s, right? So if it is too large, then you consider the same fraction. So each of the processes will have many chunks of a quantum execution time and a context switch, a quantum and a context switch. So in that case, the overall average is the average overhead ratio will basically has a limit to this ratio, because the time is too large. It's just like nq and an ns, which you take the n and then you omit it, right? And if the queue is too small, it basically you're all overhead. You're just context switching without any execution time, right? So comparison between the first come first serve and all the other ones as well here. This is important. So make sure you understand all of them. So pros for first come first serve, it has some type of fairness. You know, whoever comes first, they get served. Now the problem is that they have convoy effect. The short processes gets behind the longer ones, and it may lead to poor utilization of other resources. Remember, maybe the short burst processes are I/O intensive, right? So they might need a little bit of a time in the CPU until they can, wait for an I/O and basically keep the I/O busy, right? So, but you're always, you're now stuck on a huge process on just a processor and not using the I/O, right? So that's not good. That's not utilizing your resources, smart. All right. And shortest job first, again, it can be provable to be optimal with the waiting time, and it prevents convoy effect. Whoever comes out has the shortest, it goes then. But the problem is, first of all, it assumes that the burst time is known. This is not really easy to predict. You have to have like some schemes which are not perfect, and also it can cause starvation of longer jobs. They can wait forever, and then shorter jobs comes and keep the CPU busy. Priority guarantees early completion of high priorities jobs. So if you have a type of a system that the priorities, then this is good in this case. But the problem is that it can again cause starvation, and also how to design and assign priority values. And as we saw last session, the priority donation and the inversion, these are the things that you have to deal with. So round robin is good for time sharing because it has no starvation, good response time. All the processes get their own share, right? But there's no need to know how long the CPU bursts are. They get one after another till they're finished. But the problem is that the turnaround time gets longer, and the decision of what to be for the time quantum also is difficult to decide, right? If it's too small or large, it causes a problem. So this is an example. We're probably not going to get time, but make sure you do this. Please stay for another couple of minutes till we get the questions. But basically, you should be able to tell based on these what are and then the scheduler policy, how to draw the Gantt chart, and then also find all these values. These will be in your homeworks. You've already gotten your homework too, right? Just one thing that during this exercise you might encounter, and this is important to know. When you are dealing with a priority scheduler, the remaining burst time does not matter. When you are solving this with the shortest job first, round robin, first come first serve, the priority does not matter, right? So this is the information that is given to you to use, but you don't have to use all of them, together. And again, another example exercise. Make sure you solve this. Otherwise, you can ask questions on Piazza, or it might be covered in your recitations. So make sure again you finalize your groups and read the CPU scheduling from the textbooks for next session. Any questions?